Hey everyone, this is Dave D. Hilster. I'm your science therapist trying to get you to the land of becoming a critical thinker. Yeah, I'm not here to tell you the truth. I'm here to help you try to find it. Today we have a great talk from our third in our series with Dr. James Maxlow. But I'm Dave D. Hilster. I'm one of the directors of the CNPS. And also, you may know me because you may be on my channel a subscriber to Dissident Science. Yeah, I want to thank all my subscribers, Dissident Science. I've been super busy, but I think these interviews have been filling in quite nicely, meeting people that you've not met before, very great thinkers, people who are critical thinkers around the world. We've had numerous people on. In fact, we're lining new people up. In fact, I have just confirmed Glenn Borkert for two talks on infinity and the Big Bang. So that's going to be really great. Look for the coming Saturdays for that. And of course, today we have Dr. James Maxlow. He's still getting here. He's in Perth. I see him coming into the green room. The poor guy has to get up at what's 10 p.m. and it's way past his bedtime. He's at my age. He should be sleeping. I know, or at least in a bar somewhere drinking something. But we're really honored to have him speak again. This is his third talk in the series, and I am going to, of course, show some slides like I always do for those people who are new to this sort of format every Saturday morning. We do it at 10 a.m. on Saturday because it is the prime time. Why? Because 10 a.m. 7 a.m. on the west coast of the United States, 10 a.m. on the east coast. It's about, let's see, 3 p.m. in Europe, and you go all the way to Perth on the west coast of Australia, and you get 12 hours. So, and then you have that big ocean in between, thanks to Dr. James Maxwell. In fact, the Earth is expanded because of him. No, I'm just kidding. He's laughing right now, I know. But I always have a few slides to tell people about what we're doing here. These are Saturday science chats. They've been going on since 2008. It's sponsored by the John Chappell Natural Philosophy Society and Dissident Science. Yes, I am streaming live to Dissident Science. Hello, all my subscribers. And let's move to the next slide. There we go. The CNPS mission is to be an organization that, above all, promotes critical thinking without malice, to be an organization that supports, publishes, and promotes serious scientific work outside mainstream science, to provide a forum for open debate about modern topics in physics, cosmology, philosophy, and mathematics, to provide a forum for presenting serious papers and theories without fear of censorship. And very important, to be run and controlled in its entirety by paid membership, including the election of its directors and its members. That means they could oust me someday. Give me some time off. But anyways, it's a great community. If you want to go online, this community is hopping, man. I mean, we're lots of great discussions. I'm jumping in. This is a wonderful place. We're getting lots of new people. I'm really glad to see it. This is our new website. And you just jump in there, and the first thing you see is an activity feed of people discussing all kinds of things, people starting new groups. We got a Big Bang group for that's going to be coming up with Dr. Glenn Borkert in a number of weeks, and lots of stuff. My father and I arguing about particles and all that kind of stuff. But check it out. Please become, a member. But if you want to see what it's all about, go to naturalphilosophy.org, and you can check it out. It's active, and we recommend you try it out and sign up. So how can you participate and support? Well, you can sign up for naturalphilosophy.org. You can consider becoming a member. Very important. It's a couple $1,000s a year to do all this stuff. Even StreamYard here is $200 a year. And it really gives us all these new places to get out there in social media, because that's where everything is happening. You can sit there and not like that. If you're an oldster and say, I don't like it, I don't like Facebook and YouTube. Well, guess what, folks? That's where the world is. And if you want to get your information out there, if you got great work to show, that's where they are. Also, you want to participate in our community discussions on our website, just log in. We do ask you to put a photo. You have to put your real name in a photo. If you don't do that, we do not allow you, because we do not like anonymity, because that's one way people on social media can go in and just wreak havoc. We believe in our philosophy, and our rules is face to face combat in the good sense. And we need a picture of you and your real and full name. And people have been cooperating because they want to get out there. And also, of course, you can post news and happenings on social media about us, share our links, subscribe to our YouTube channel. Our websites, of course, are naturalphilosophy.org. If you're really new to this, check out sciencewoke.org. Man, we've got a lot of views on that, a lot of great articles. It's online magazine for critical thinkers. And if you don't know what's wrong with mainstream science, we even have a place, all the problems with mainstream science. You can click on that and read all kinds of articles about it. If you're a writer and you are in the dissident community or critical thinking community, you want to be part of that, we're always welcome to new people writing for that magazine. Of course, we have a wiki as well, wiki.naturalphilosophy.org. Uses the exact same software as Wikipedia, which is open source, called MediaWiki. And we have over 10,000 pages there. And so you can find quite a lot of stuff there. And coming are Chappelle University courses in natural philosophy. We founded that in 2018, and we've got one person already writing courses for that. And if you have a course you'd like to write about, in fact, our guest speaker today and a member of our group, actually a Lifetime Achievement Award winner. That's the least we can do, is Dr. James Maxlow, and he is going. He better teach a course, because for some reason the universities aren't letting the expansion tectonics in. So you want to be checking that out. That's coming in the future. Just a couple of commentary. I've done this one before. Why do we support everyone? It's not. It isn't the. Isn't there only one accepted model? People say, yeah, I mean, all science, we all accept the periodic table. Yeah, we do, but we're right now in a science revolution, because universities do not do that. If you go to university and you want to write your thesis on expansion tectonics, good luck. Why is that? Well, it's because universities don't major in critical thinking. They major in dogma. They major in telling you what the truth is. And if you don't follow that truth, then you're no good, especially in physics and cosmology. A lot of other tectonics, plate tectonics, same thing. Change comes, of course, from dissent and not from groupthink. CNPS gives a platform to everyone who's in that boat, and not from groupthink, of course. And history decides all this, folks. Everybody should be out there, of course, doing their stuff, but we don't decide, nor do the universities, nor do the science evangelists or the journalists. And as Dr. Alexander Unsker, which I hope to get on here, he is an amazing person. If you haven't read his book, The Higgs Fake, read it. If you think that they're doing real science in particle accelerators, think again, guys. If you sent NASA scientists or SpaceX scientists to the Large Hadron Collider and had them sit down and evaluate the way they do stuff, they would be thrown out in about 10 minutes. So read Alexander Unsker's stuff, and like he says, just keep working on what you're doing. So that's my commentary. Oh, this is actually 3. I'm sorry. Expansion. I should have saw that part, but this is expansion tectonics 3 out of 4 with Dr. James Maxlow. If you don't know who he is, he's a retired professional geologist who worked as a mining and exploration geologist throughout much of Australia. So yeah, he knows geology. During that time, he returned to Curtin University of Technology in Perth, Western Australia, to study and research expansion tectonics. He was very lucky to be able to do that, and from this research, he gained a Master of Science degree, and in 1995, followed by a PhD. Amazing. And if you haven't seen it, he has asked me to tell you about this really great site, expansiontectonics.com. Where do you go for expansion tectonics? Expansiontectonics.com. Here's the front page here, homepage of the website, and all those amazing models there, just chocked full of stuff. So, and also, he wrote, in my opinion, the most important book in geology ever written, and he's the most important geologist ever written. Oh, yes. Actually, he's a deep fake. He doesn't exist. We've invented him in the AI labs. And what you're seeing today is, no, I'm kidding. Now I'm going to have 1,000 people here claiming that this is all fake. It isn't fake, believe me. Because sometimes if you ask a question that he doesn't like, because that's a weird question, that deep fake wouldn't do that. So this is a real live guy, amazing, amazing mind. So if you haven't checked it out, Beyond Plate Tectonics, you notice he doesn't say, he could have been less polite in that title, I'm sure. Beyond Plate Tectonics signposts that this is something more advanced than basic academic courses might cover, while the subtitle of Unsettling Settled Science confirms our suspicions about the book, of course. The whole book is all revolutionary and new, unsettling to anyone who thinks there will be no more major revisions in earth science. Is that the understatement of the century, maybe of various centuries? It is just as stimulating to those people who understand that scientific discovery will never be finished. Of course, I'm now going to bring up the man himself, Dr. James Maxlow. Hey, James, how are you doing?
Yeah, good. Thanks, David. Yes, I've just unmute. I'm not a robot. I just pressed the "I'm not a robot" button.
Well, what's really amazing today is you can take anybody and live now put their face up there and get their voice and just say what you want. I've never tried it, but I may do that. Maybe I'd like to do and get Einstein up there and then talk about how his theory is wrong. That would blow people's minds. So, but I'm really amazed. Like I said, you're an more oldster like me in your 60s, and yet here you are with decent lighting. Your face is well placed in the picture here, and you have, I guess, a nice microphone and two screens. This is. If you would have told me, yeah, if you would have told me this about James Maxlow about a year ago, I would have laughed my head off. But you are welcome to the age. I'm going to let you go forward with this. I just think, is this a mere coincidence? That's what the title of your talk today, correct?
That's correct. Yes.
Okay, why don't you get your screen ready to share here while we wait for him to get that screen, and then I'm going to throw that up with him and get that moving along. But he'll be talking again about mere coincidence. So do I need to do anything for you? Let's see. Can you share your screen?
I've just allowed. Yeah.
Okay, all right, good. I'm going to remove this here. Okay, we see it. So take it away, Dr. James Maxlow.
Okay. Hello, everyone, and welcome to my third of 4 podcasts on expansion tectonics. In my previous 2 podcasts, I focused on modelling seafloor and continental crusts in order to create spherical scale models of the ancient Earth, extending from the present day back to the Early-Archaean, plus one model at 5 million years into the future. From this research, it was concluded that the extensive geological mapping evidence and empirical modelling studies more than adequately demonstrate that an increasing radius Earth is indeed a viable and demonstrable tectonic process. This is all very well, but as Shields so astutely mentioned in 1997, ultimately world reconstructions must be congruent not only with the data from geology and geophysics, but also with palaeobiogeography, paleoclimatology, and paleogeography. What this means is that if the primary global observational data do not fit the small Earth models, then it is the models that must be wrong, not the data. Until now, this modern data has only been investigated from a conventional plate tectonic perspective. And unbeknownst to most people, if the data doesn't fit conventional plate theory, then ad hoc theories are generally proposed to make the data conform. The primary focus of this, and my following 4th talk, will be to show you a selection of modern global observational data utilised in my research studies to highlight how this data interacts with the small Earth models, as well as what this data has to say about the formation and subsequent geological history of the Earth. I must once again emphasise that the research presented here is a data modelling exercise, not a theory modelling exercise, which will focus on modelling modern global observational data independently of any present or pre-existing theory. Previous crustal modelling studies have shown that on an increasing radius Earth, until about 250 million years ago, there were no modern oceans, only ancient continental seas, about here. During that same time, continental crust existed as a complete crustal shell encompassing the entire ancient Earth. The outlines and configurations of the exposed lands making up the supercontinents were then dictated by the presence of and changes to these ancient seas. The transition from ancient seas to modern oceans came about when the Pangaean supercontinent first started to rupture and break up during the late Permian, some 250 million years ago. Small Earth modelling studies show that the volume of ocean water has also been increasing steadily since Archean times, and most prominently since crustal breakup and opening of the modern oceans. It is suggested that this increase in volume of water occurs in conjunction with intrusion of new volcanic seafloor crust along the newly established global network of mid-ocean ridge spreading centres. This new water, as well as accompanying atmospheric gases, is inferred to represent escaped volatile elements which occur naturally within the crystal lattices of all molten volcanic rocks. Complicating this geographical process is that major changes in sea levels also occurred during merging of two or more ancient continental seas, as well as breakup of the ancient supercontinents and opening of each of the modern oceans. Major changes in sea levels then represent a realistic mechanism for periods of mass extinction of ancient plant and animal species. On all pre-Triassic small Earth models, the ancient crusts existed as a complete continental crustal shell encompassing the entire smaller radius Earth. Prior to the early Triassic times, exposed supercontinental lands were defined by a superimposed network of continental seas coinciding with sedimentary basins. The primordial Archean supercontinental assemblage is shown here, along with the Archean equator and poles located using published paleomagnetic pole data. Shallow continental seas were present during this time, which coincides with the distribution of khaki-coloured Proterozoic orogenic rocks shown on this image, these colours here. The named remnants of the present-day modern continents are also highlighted as black lines. During these Early-Archaean times, it is envisaged that once the primitive crust had cooled and stabilised, an increase in Earth radius then initiated global-scale cracking and fracturing of the crust, localised primarily within a network of orogenic activity and crustal weakness. This network of crustal weakness and fracturing was subsequently intruded by renewed granite magma or intrusion of primitive volcanic lava. The tonalite trondhjemite granodiorite group of granite rocks common to all Archean terrains throughout the world may be related to this event. During the latter part of this primordial supercontinental phase, Proterozoic sedimentary basins were slowly filling to capacity over the extremely long period of time operative during these ancient times. These sedimentary basins and relatively shallow seas are again shown as khaki-coloured orogenic rocks on this image. These geological changes then evolved imperceptibly into the better-known Rodinia supercontinent. Rodinia is represented here by the late Proterozoic small Earth model at about 800 million years ago. The assemblage and distribution of the remnant modern continents are again shown as black outlines, along with the Proterozoic magnetic poles and equator. The Proterozoic in particular is characterized by the presence of very large, stable sedimentary platform basins, forming relatively shallow seas with a low elevation contrast between the dry lands and the seas. During these extended Precambrian times, the ancient North and South Poles were located within what are now northern China and West Africa, respectively. West Africa, China. Similarly, the ancient equator passed through what is now North America, East Antarctica, Australia, Greenland, and Scandinavia. As can be seen from both the Archean and Rodinia small Earth models, the change from one supercontinent to the other is progressive and evolutionary, and this theme will continue to follow through to the following Gondwana and Pangaea supercontinents. Gondwana is shown here, reconstructed on the Ordovician small Earth model at about 460 million years ago. In this figure, the distributions of ancient continental seas, plotted from published coastline geographical data, are also shown as shaded blue areas, and the various ancient continental seas and supercontinents are located and named. On small Earth models, during Gondwanan times, the Earth was undergoing a steady to rapid increase in radius and surface area, and was also fast approaching crustal rupture and breakup. This Gondwanan crustal assemblage retains the same configuration of cratons, origins, and basins as seen on the earlier Rodinia and Archean supercontinents. The only difference being the greater surface area of surrounding sedimentary basins and hence aerial distribution of continental seas. This crustal assemblage is retained still further in time until initiation of crustal rupture and breakup of the pan-global continental crust during the late Permian times. During Gondwana times, the small Earth South Pole was still located within central West Africa, down here, in what was then South Gondwana. The North Pole was also still located within northern China, in what was then part of the Tethys Sea. The ancient equator passed through East Antarctica, Central Australia, North America, Central Eurasia, and India, through what was then North Gondwana. The late Paleozoic to early Mesozoic times coincided with breakup of the Gondwana supercontinent, and it was accompanied by draining of the continental Tethys, Panthalassa, and Iapetus seas as the modern oceans began to open. As a result of draining of these seas, each of the Gondwana and related supercontinents geographically merged with the smaller Laurentia, Baltica, and Laurussia subcontinents and to form the more familiar Pangaea supercontinent, shown here on the Permian small Earth model. This figure again shows the continental seas as shaded blue areas, and the various supercontinents and intervening seas existing at the time are also named. Following rupture of the supercontinental crust, Pangaea eventually broke up during the late Permian and dispersed as the modern continents during Triassic to present-day times. This post-Pangaea interval of time also saw large apparent shifts in the location of the North and South Poles and equator, occurring as a direct result of opening of the modern oceans and apparent migration of the modern continents. Paleomagnetics is used in conventional studies to establish an apparent polar wander path for each crustal fragment in order to constrain positioning of the fragmented crusts during assemblage on a static radius Earth. The modelling studies presented here do not generate apparent polar wander paths and hence do not rely on paleomagnetics to constrain assemblage of the ancient crusts. These modelling studies and assemblages are instead governed solely by geology. The locations of present-day to Archean magnetic poles, shown here on each of the small Earth models, were located using data from the International Paleomagnetic Database of McElhaney and Locke, 1996. Plotting this data on each small Earth model consistently shows that approximately 95% of the pole data plot within 25 degrees radius of each diametrically opposed magnetic north and south pole location. The small Earth model shown on this and the following figure are centred on the north and south poles respectively, and also include the anticipated polar regions, shown as shaded blue circles. It is significant to again note that the distribution of mean north and south poles, plotted independently on each small Earth model, show that each pole plots as diametrically opposed north and south poles, with no requirement for apparent polar wander, as they should do. The magnetic North Pole is shown here, located in northern China, and it remained throughout Precambrian and into early Paleozoic times. These models here. As the Pangaean supercontinent ruptured during the late Permian and the various northern continents slowly migrated south, the distribution of North Pole locations shows there was then an apparent northward migration of the magnetic pole through Siberia to its present location within the Arctic Ocean, down here. Similarly, the magnetic South Pole is shown located in West Central Africa, and it remained there throughout the Precambrian and early Paleozoic times. As the Pangaean supercontinent ruptured and the various southern continents slowly migrated north, the distribution of South Pole locations shows there was an apparent southward migration of the South Pole along the South American and West African coastlines prior to crossing the opening Atlantic Ocean during the Mesozoic times and moving to its present location in Antarctica. So it's shown here migrating down the west coast of Africa, across the Atlantic Ocean, then on to Antarctica to its present location here. As well as plotting magnetic pole data, ancient latitude can also be plotted from paleomagnetic site sample data. The data shown here was sourced from the International Global Paleomagnetic Database of Pozharevsky 2004. This data is unique in that ancient latitude calculated from site sample data represents the actual latitude of the ancient sample site, and, unlike magnetic pole data, does not require projection beyond the sample site location. Latitude data is shown here plotted on each small Earth model, extending from the Early-Archaean to the present day. In this figure, the calculated latitude data is color-coded to represent data located within the north and south equatorial climate zones, shown as red dots, the north and south temperate zones, shown as green dots, and the north and south polar regions, shown as blue dots. The climate zone boundaries, shown as dashed yellow lines, are based on boundary distributions on the present-day Earth. Considering the increasing uncertainty in structural correction and magnetic screening of site sample data when moving back in time, the latitude data for each small Earth model shows a very good correlation with each of the climate zones, in particular for the Cenozoic and Mesozoic eras. These ones here. From the established pole and latitude locations, it is then possible to model the expected climate zones for each of the north and south polar regions. This figure shows the anticipated North Polar region, centered over the ancient North Pole, located on each of the small Earth models. Also shown is the distribution of known glacial-related rocks and formations, shown as red dots, as well as the presence of known ice sheets, shaded white. It is significant to note that on these small Earth models, the distribution of both the glacial-related rocks and ice sheets coincide with the highlighted major glacial events, as they should do. These glacial events here, here, and here. The absence of ice sheets over the North Pole during the Permian and Carboniferous periods, these ones here, is shown to be the result of warm Tethys sea-related currents circulating from the equatorial regions into and across the North Polar region. This North Pole observation is further quantified by the abundance of warm water marine fossil species present throughout the Tethys sea regions, to be highlighted in my next podcast. This next figure shows the locations of the anticipated South Polar region, centred over the ancient South Pole. By definition, the North and South Polar regions must remain centred over each of the ancient poles. During migration of a continent into or out of a polar region, if conditions are favourable, the leading edge of the continent may then begin to establish an ice sheet as it enters a polar region, or the leading edge of an established ice sheet may melt as it moves out of the respective polar region. Similarly, the trailing edge of an existing ice sheet may also freeze and increase in surface area as it moves further into the respective polar region. This is highlighted by the passage of Antarctica into the South Polar region during the Cretaceous to present day times. These ones here, where a permanent continental ice sheet was first established over Antarctica approximately 33 million years ago. We will also note that during the Ordovician, Carboniferous and Permian times, these ones here, here, here and here, the South Polar region was located over the exposed Gondwana supercontinent, and hence, unlike the North Polar region, had permanent ice sheets during these times. In my next podcast, I will continue to use these small Earth models as a platform to generate additional global observational data in order to further quantify the outcomes of this modelling exercise. Following on from my previous podcasts, where I briefly touched on a proposed causal mechanism for increasing Earth radius and mass, we are now in a position to speculate further on the formation of the Earth and Moon. The modelling studies presented here have shown that the size of the Early-Archaean Earth was around 27% of the present Earth radius, a similar size to the present Moon. Geological studies tell us that at that time the entire primordial Earth crust comprised granite and volcanic rocks, with very little sedimentary rocks and no large oceans. It is speculated from crustal and mantle temperature studies by others that the pre-Archean Earth, that is, times older than 4,000 million years ago, may have been incandescent. These studies show that during these pre-Archean times, the Earth was hot enough to remain molten. By about 4,000 million years ago, the Earth had cooled enough for the molten crust to start crystallizing to form rocks, and also remain stable enough to eventually form a solid crust. During the distant pre-Archean times, which was an indeterminate time span of maybe billions of years, it is speculated that the Earth-Moon system may have originally been a single molten planet, shown here at far left. By combining the volume of the present Moon and the volume of the Early-Archean Earth, the pre-Archean Earth-Moon system is readily calculated to have been approximately 2,100 kilometres radius. At or a short time prior to 4,500 million years ago, which is the age of the oldest moon rocks, the Earth and Moon then separated, shown here. It is envisaged that this separation may have been a result of gravitational instability of the more basaltic molten surface layer of the primitive Earth-Moon, occurring as a result of high rotational velocity and centrifugal forces. This separation then formed a double bimodal planet. This mechanism is described in conventional literature as fission of the Moon from the Earth's primitive basaltic crust through centrifugal forces occurring during a period of high angular momentum of the Earth-Moon system. It is further speculated that once separated, this bimodal planet scenario would have comprised two bodies, the Earth and the Moon, of approximately equal size, around 1,700 kilometres radius. Currently, the Earth and Moon are moving apart at a measured rate of 38 millimetres per year. This more passive separation process, in contrast to a speculative impact event, may then go a long way to explain why the Moon is currently in synchronous albeit retrograde, rotation around the Earth, always showing the same face to the Earth. Similarly, this speculation is further supported by research in 2001, where a team from the Carnegie Institute of Washington found that lunar rocks gathered during the Apollo program carried isotopic signatures that were identical to rocks found on Earth. Similarly, in 2012, analysis of titanium isotopes from surface lunar samples, and in 2016 from oxygen isotopes, further indicated that the Moon has the same composition as the Earth, and the two bodies are indistinguishable. This conflicts strongly with the current speculation that the precursor to the Moon originated far from the Earth's orbit, and the Moon was formed as a result of a giant impact between the Earth and a Mars-sized body. Not only is this isotopic signature data saying that the Moon did not originate from debris left over after, or fusion of, a giant impact between Earth and a Mars-sized body, it is also saying that the Moon and Earth may not have been involved in heavy bombardment from asteroids or comets colliding with the Earth and lunar surface. Debris from foreign asteroids or comets would have been readily detected in the research carried out by the Carnegie Institute by showing distinctively separate bipolar isotopic signatures, which it clearly doesn't. On an expansion tectonic Earth, during the speculated Earth-Moon separation process, it is envisaged that the hotter primitive core mantle, as well as remnants of the surface layer of the former Earth-Moon body, remained intact, forming the primordial Earth. After gradual separation of the Moon, it is further envisaged that there would have been a period of time when remnant spatter of fragments left over from this separation process would have bombarded both bodies, forming the now familiar cratering on the near side of the Moon's surface. Much cooler temperature conditions on the Moon may also explain why the primitive Moon cooled and crystallized 500 million years earlier than the primitive Earth, thus preserving this period of surface bombardment and cratering. Once the Earth-Moon body separated, if that indeed occurred, it is speculated that the remaining molten core mantle material forming the primitive Earth then began to differentiate, whereby the remaining molten elements and minerals separated into a distinct core and mantle. Over time, surface temperatures then gradually cooled sufficiently to form and preserve a new primitive silica-rich outer crust. On Earth, during this differentiation process, the expulsion of fluids and gases from the mantle then began to accumulate in low-lying areas. This accumulation initiated formation of small, shallow seas, and the gases rose to form a primitive atmosphere, with an accompanying further reduction in mantle temperatures over time. Since then, the size of the expansion tectonic Earth is shown to have increased exponentially to the present day. Thank you for your interest, and for those seeking more information on expansion tectonics, please visit my website or contact me at my email address shown on screen. Thank you. Over to you, David. Sorry, David, I can't hear you.
Sorry about that. I keep myself muted during the time, so people don't hear me typing. We had a lot of interest and a lot of chatter during your talk, but I think I don't know if you've ever heard of it. There's a guy on who is a proponent of expansion tectonics, a young lad who claims he actually is making a model of expanding Earth by using small spheres and increasing those and doing some interesting modeling, physical modeling of it. And one of the things he did was, there was numbers of people doing that, which was really quite fascinating. And it's always great to see people trying different ideas. But one of the things he mentioned a couple of years ago was he claimed to have calculated the probability coincidence of all the continents fitting together on a small orb, and the number was like 96 trillion or something like that to
Now
one.
just extrapolate that to assembling the most ancient Archean and Proterozoic crusts together to form a complete shell. That then it becomes mind-boggling.
Yeah, that is truly
And then have
amazing.
all the poles and the equators and all that match up.
Yeah, you get to a point where you can't even. I try to explain. You know, you always want to try to take the other side, right? After a point you can't anymore because you can't. There is no other explanation. You just can't explain it in a different way. I mean, how coincidental is just taking the current Earth and taking away the crust, the ocean floor, according to its ages, and everything seals up into a ball. I mean, that to me is how do you explain that away? I think one of the things is there is a geologist in our group. I won't say who he is, and he is actually a fantastic guy and has a fantastic stuff in other areas. But you know, when some of these geologists make a living at subduction, and so they go around, and they tell people where they can make their buildings and all that. But I think the interesting part is that even these people I've heard say, well, the evidence is quite good. But if you go out into the real world and say, I'm using expansion tectonics to do any geological work, depending on where you are, that could be really fatal. But one of the people I wanted to ask you about in that area, in that vein, is Doctor. I think it's Giancarlo in Italian.
Yeah, John Carlo. Yeah,
Giancarlo. He,
yeah.
from what I understand, I read many, many years ago. It was in the beginning of the 2000s when I was reading and found out about expansion tectonics. He seemed to have used expansion tectonics in his geological work. Is that
He's
true? Or
he's a geophysicist,
right? Have
and
you
he
heard
has, yes,
about?
he's
Yeah,
written
can
a
you
number.
explain? Yeah, can you explain that? Because that's interesting. Because when you have a theory, right? If you can actually use that theory to your advantage better than the plate tectonics, that's one more proof for that's a better model.
Yeah, I
Can you
don't
explain
know
that?
too much about him, but I have met him a number of times, and I've presented at a conference in Sicily that he ran. He's a physicist at the institute, one of the institutes in Rome, and he's been an advocate of expansion tectonics for many, many years and written quite a few papers on the subject. He has to, because he works at the university, he has to toe the line to a certain extent. But fortunately, he's been given the freedom to follow his passion, like myself. And he has published a number of papers describing the geophysics around the Mediterranean region. Of course, the Mediterranean, as we've just recently heard on the news about the earthquake in wherever it is, yes, just recently, that is a very seismically active region of the Earth. And both he and there's another fellow from in that same area also has published a number of papers dealing with earthquakes and seismic activity in that area.
So it's a case when you're looking at, is this a mere coincidence that in reality it's become, in my opinion, it's become so hard if you really look into it with your critical mind that this would be wrong. But people actually are using it where they can. And have you used it in the field? Have you made discoveries? When you think of the time before you were expansion tectonics, right? Tectonicist. Now you are. Do you see things differently as a geologist when you go out?
I certainly do. Um, um, Plate tectonics, in my 40 plus years of pre-retirement professional life, I never once used plate tectonics. Never once. I came across it a couple of times with other people studying areas that I'd been mapping and exploring, and they're all basically wrong. The data was being forced into a preconceived plate tectonic model. But no, I've never used that. If I was where I am now, during the 1960s, you and I would be extremely wealthy people because I would have been able to predict the locations of some major world-class mineral deposits throughout
We
the
would be
world.
rich, is what you're saying.
Focus exactly where to go. But unfortunately, during that time, that 60-year time interval, these major world-class deposits have been discovered. So my work just substantiates where they are and where they are in relation to other deposits, fitting countries together like so. You get mineral deposits on these continents. For example, your west coast of North and South America tucks in against the east coast of Australia, and we get very similar porphyry style gold, copper, molybdenum, silver deposits up and down our east coast, as well as the Americas. One of Newcrest Mining that I worked with prior to retiring, they had major mines in New South Wales with the same porphyry style mineralisation, world-class deposits as you get in the Americas.
Yeah, I mean, it's quite amazing that if
Sorry, I just finished that.
Go ahead.
In a plate tectonic scenario, the two don't match. So
Why is that? Why is that?
They don't assemble them together as I assemble them on my models. So the bits and pieces of it that don't match.
I think another interesting part of your talk today was you're talking about the moon. That certainly generated a lot of chatter because, of course, we've heard about the moon being, in the beginning it was just sort of these masses that all came together, and Earth came sort of swirled and got together, and the moon did, and they happened to be in orbit, or maybe one gas turned into sort of like a galaxy where you see a little swirl and a bigger swirl. The latest today's science, cosmology likes this idea that something came along and smashed it. They've got all the 3D graphics, and you see it 100 times, and all the science evangelists are out there preaching all this. And I think it's interesting. We have a lot of questions. I have a lot of questions myself. Why if I understand right, you're matching the properties of the moon, the rocks on the moon, to a certain time. Is that what you did, or is it? How did you come up with the idea? I know you said it, but maybe explain it again. How did you come up with this is the time where this happened, and did you give a reason for why it actually broke off, or because it was all one mass, is what you're saying? Is that correct?
Gravitational instability.
Yeah, right.
Yeah, it's an area that during my PhD studies, I was warned off speculating too much about origin of the Earth, Moon, and mechanisms and all that. But what I've found throughout my research that you just can't afford it. You have to form an opinion. And with expansion tectonics, with all my modeling studies, all of the data that I use the raw data and drape it onto my models to see what the data is telling me, not the other way around. I don't use the data to fit the theory. I use the data to tell me what it's trying to show me. And from that, I was able to work this data back in time with all the data that I used, the fossils, climate, sediments and minerals and oil and gas and all sorts of things like that, but work it back in time to see how they physically relate to each other back in time, and what were the major events occurring during those specific times to have formed these oil and gas, for example. Minerals are another example. Why did they all occur at that particular moment in time? Working these back in time, I then got to the point where you have the Early-Archaean model, the first model that I got back to, the oldest model I got back to. All of these rocks are granites and volcanic rocks. Granites and volcanic rocks form under extremely hot molten. They were molten at a time. So, and all our age dating of rocks throughout the world go back to approximately 4,000 million years ago, 4 billion years ago. It's a sprinkling either side of that, but approximately the 4 billion years ago. So you go, why aren't we seeing older ages older than the 4 billion years, like we are seeing on the moon? The moon is 4,540 or something other million years, a billion years, 4.54 billion years. Why are we not seeing those older 500 million year interval of time on the Earth? And that's where I came up with this concept that the rocks tell me that the Earth was molten at or around or prior to 4,000 million years ago. So what was happening to the moon? And then it just through literature studies, I came up with that fission model that has been presented by other scientists many years ago, probably in the 70s or 80s, from memory. And it was foo-farred in favour of these extraterrestrial impact events and asteroids and meteors and small planetary bodies. And as I pointed out, the isotopic isotopic signatures are like DNA. DNA of if you take a DNA of myself and a DNA of my brother, they match up. We're from the same parents. The isotopic signatures of the Earth and Moon demonstrate that they are the same origins. If there was a small planetary body that hit the Earth at some stage and fought to form the Moon, then there would be evidence in that isotopic signatures that there was a different. Came from a different extraterrestrial body. Same with the meteors and comets and such like that are proposed for the bombardment and craters on the Moon. The isotopic signatures are telling us that the Earth and Moon are one and the same. So that's where I came up with the concept of pre-4 billion years ago Earth. It was molten. What was happening with the Moon? So I combined the two and came up with this single Earth-Moon body. The outer crustal layer of that primitive Earth-Moon body was essentially basaltic lava, much the same as our seafloor crusts now, which is a mantle material. This material was molten, speculative of course, speculating that this material is molten. When you rotate a molten body at high speed, relatively high speed, then you potentially get instability. Instability will generate a wobble. A wobble will then form a dumbbell-shaped planetary body, and then ultimately separation of that body, and hence the rotation of the Earth-Moon as we have it now. That's how I envisage it. I don't take it beyond that, but in my publications, I briefly talk about the potential that the molten Earth, combined Earth-Moon, originated from the sun. And I'll leave it there because that is taking speculation beyond speculation.
You don't have any rocks from the sun?
No. Well, maybe. We've got one here. We're standing on one, if my theory is correct. As well as the other planets within the solar system. I maintain that they were ejected from the primitive young sun, periodically ejected, similar to our sunspot activity that we see now on a much reduced scale now, of course. But it's one area of research that could be delved into, and this would mean that the Earth-Moon system is also, as well as moving away from each other and all the planets, they're also moving away from the sun. over time. So your centrifugal forces, your
Yeah.
planetary motion, etc., is all changing over time. I haven't been able to resolve the maths involved in that. I'm not clever enough to do that. I like licking rocks myself, but still. There is, or during the 70s, there was a lot of effort put into rhythm. What's the term? I'm having a senior's moment here. Sorry.
No, that's okay.
Seashells, the seashells and whatnot. The sea creatures, they secrete a shelly layer on a daily basis,
Right.
and over that, the moon, the moon, the 30 odd days of the moon cycle, you get a recognisable pattern of bands, same as tree growth, etc. Your winter, summer tree growth. You get, you can then determine the length of a moon cycle, for example. Then you can combine that and form a solar cycle, etc., etc. But there was a lot of effort put into that by a number of people in the 70s, but it came to nothing. Well, they deduced that the length of the day was different than what it is now. I can't remember which way around it is. Sorry, I can't remember which way around it is, but it doesn't matter. But what I concluded, I tried to crack the maths involved and get it tied in with my research. But what I found was you have to make an assumption, and that is the assumption that the solar cycle is constant. And then you can work out your moon cycles and your daily cycles and so on. And so you have to make an assumption, and that's not what expansion tectonics is all about.
Oh, that's what plate tectonics is all about.
Yeah.
Here's
Regarding
here's
this question, why hasn't
here.
the moon expanded? The reason it hasn't expanded is because the moon took all the basalt, and the basalt has already expanded, whereas the Earth retained its core mantle. And it's the core mantle which is your very complex physics, and that's where your magnetics is, drawing in solar particles from the sun and expanding with time, whereas the moon has a very, very weak magnetic attraction and can't absorb these solar particles anywhere near as much as the Earth can. So it effectively took the dead skin off the ancient Earth-Moon system, and there it stayed for there ever and a day.
Wow, that's
we're currently generating a new basaltic crust, which equals the seafloor crust. What people don't appreciate and realize is that the seafloor crust is actually exposed mantle. We talk about when the geoscientists talk about the crust, they talk about the continental crust and the seafloor crust as if the crust was something unrelated to the mantle, and then below that is the mantle. But in actual fact, the seafloor crust, the basaltic crust, is actually cooled and quenched and cooled the mantle crust.
Yeah, I've got some other questions as well. Moon expanding was one a very if it is expanding extremely small is what you're saying, right? And I think
it's that goes the same with the most of the rocky planets of the solar system. They have very weak magnetic attraction, whereas the giant planets, the Jupiter, Saturn, Neptune, etc., all have high to extremely high magnetism.
Right.
And Earth is in that. The Earth to me is a transition from the rocky planets to the giant planets, and ultimately that form a giant planet.
Yeah, that's very interesting. And the question becomes, does a Jupiter then ignite and become a sun and all the moons become planets?
That's exactly right.
Yeah, I have another couple questions even from myself. One of the things I is about oil. You were talking about like petroleum or that. Now, the explanation, we call them fossil fuels. And when I hear that word, I'm not sure that's the real, what's
The
really
real term
how
is
it,
hydro,
right. So
hydrocarbon.
what people, right. And so when we call them fossil fuels, that's a misnomer. They're more what people would call abiotic. They really didn't come from a life form. Is that correct?
Biotic. You're referring to biotic. Fossil
Right.
fuels is
Yeah,
biotic.
but there's a word abiotic. So
That's
oil is
correct.
abiotic then.
Yeah. Yeah. I'll take it from there, David. Um, if you go back beyond, well back beyond, back in time, beyond the Permian, Carboniferous Permian, or actually beyond, say, the Archean, not the Archean, beyond the Cambrian, 540 odd million years ago, there was essentially no life forms, but there was an abundance of carbon in the sediments. The Paleozoic times are renowned for black carbonaceous shales. At the Telfer gold mine where I worked here in WA, that was those regional sediments were a billion years old, and we had black carbonaceous shales. So that is primary, and even into the Archean in South Africa, they have the black carbonaceous shales. And this carbon is primary carbon. Once you get the life forms starting to appear and evolve, they use that primary carbon in their physical makeup, their chemistry, biochemistry. They use this in their chemistry. They other creatures came along and gobbled them up, used their carbon, hydrogen, oxygen, basic compounds into their own body structure and chemistry. They died, evolved, and etc. Died, fell onto the bottom of the ocean, etc., and accumulated. If they get covered over, they get preserved, and that's where your oil and gas comes from. They get preserved in time, heated and preserved in time. But if they are not covered up and preserved, they are recycled. So your primary carbon is keeps on recycling over and over and over and over to now. You and I are essentially recycled carbon, etc., from past history. The abiotic concept comes from very ancient oil and gas deposits, mainly in Russia from memory, where the chemistry, the chemicals, petroleum based hydrocarbon based chemicals were derived essentially from these primary carbonaceous sediments. During the Permian and Carboniferous, 250 to 350 odd million, 400 million years ago, there was a very rapid surge in evolution of plant-based and insects and so on based material over that period of time. Very relatively stable sedimentary basins and accumulation of an enormous amount of organic matter, and these were covered over and preserved as our fossil coal fuel deposits. Yeah, let's see, which way around is it? Oil and gas accumulates differently, forms differently to coal. Coal forms where you get a lowering of sea level. The coal is formed in the shallow regions and is covered with sediments, whereas oil and gas forms when the sea level rises and the accumulated material on the bottom of the seafloor is covered over and preserved in those environments. Most of the coal it occurs within this Permian and Carboniferous periods, whereas the most oil and gas, or much oil and gas, in particular gas, comes from the late Cretaceous period, and that's again in a varying sea level period of time. So getting back to your original question, you have your primary carbon within your carbonaceous sediments that gets used by these primitive organisms, and then the carbon gets recycled over time. And so biotic and abiotic hydrocarbons are perfectly feasible, and they both occur and both feasible. Having said that.
Yeah, it's a complicated situation then.
But
And
just
then and
very much sorry that there was an abundance of carbon in the sediments prior to
right,
that.
right, right. So another question I have is what we are actually extracting those, of course, and using those. Are they being produced today?
In
Methane,
theory, yeah.
gas, oil?
In theory, yes. Yeah, they're accumulating, yes, in
Okay.
swamp gas and peats are modern day equivalent. Peat is a modern day equivalent of coal, very primitive coal. You go peat, brown coal, black coal. So peat is what's forming at the surface now. It's spongy. It will burn, but it's very low grade. Brown coal is peat that's been buried and squashed and dried in time, but it's not buried. It hasn't been heated and cooked like the black coals. The black coals are deeply buried, heated and compressed over an extended period of time. So the black coals are the better quality coals. So yes, they are occurring now. And the gases, of course, are just your swamp gases, your methane you find in the swamps and those sort of environments. So they are accumulating now, still accumulating, but not necessarily the amount that was being accumulated in, say, the Permo-Carboniferous.
So yeah, so one of the things is that we're saying we're depleting the supply, but in actuality, it's being built today. But of course, we don't hear that, and we're not taught that. It's sort of like it
Not
happened
accumulating.
once.
Yeah,
Well, I
not as
mean,
much as what we
well,
use.
sure, sure, exactly. But I'm saying though is you're not taught in schools that the Earth is still producing this. We may be extracting it way faster than it's producing, but you don't hear that, right?
No, certainly
That's
the
just
black coals are not being produced
right.
now as it was, because the sedimentary environment conditions were totally different. That was prior to breakup of the Pangaean supercontinent and opening of the modern ocean. So those environments just don't exist to the extent they used to now compared to what they used to be.
Right. Now, one of the things I've thought about over the years since I've, found out about the idea of expansion tectonics and all the data that supports it, as a geologist, how fortuitous do you see that the water content of the mantle seems to not be, yeah, there's more water coming from the mantle, meaning the sea is rising according to you as a geologist. But it seems really fortuitous in some sense that this has not, because otherwise we would be an aquatic planet. That the amount of water, is this a natural consequence of our atoms and the way the atoms make up the mantle and how much water it can hold? Or is this a fortuitous thing that happened on Earth?
I'm only speculating here, but the deeper you go down, the pressures and temperatures become extreme. So what we think of water gas molecules probably don't exist. They're probably disassembled into oxygen and hydrogen and chlorine and carbon and calcium and so on and so forth. So you're getting these elements within the crystal lattices of other minerals and whatnot. when you when you come up through from mantle to crust, when your depths become the same material, if you bring your material up further close to the surface, these what we call high-grade metamorphic rocks, which are subject to very high temperature and pressures. When you take that material, bring that material into a different environment, lower pressure, lower temperature, then the minerals making up these rocks then alter. They alter to minerals that are more stable in these changing environments. And these same minerals, when you rearrange these minerals, you also get other elements, that say the oxygen and hydrogen, etc., devolatilizing off these elements, and of course recombine to form your water and gases. In my book, I describe probably about 8 or 10 elements, gases and various elements, which naturally occur within the crystal lattices of various minerals, and these high temperature minerals. And once you change these minerals through metamorphic alteration, you then liberate these minerals and these gases, which the water and gases of the ocean atmosphere essentially come from the mantle. And that's the same, very similar process. You're moving from your dunites to your dolerites and basalts. The higher up you go through the food chain. And basaltic rocks in particular, in fact, essentially all volcanic rocks contain upwards of 15 to 20% weight by volume of volatiles. As I mentioned in my previous podcast, it's like a bottle of soft drink, where your carbon dioxide is dissolved in your drink, and when you peer through it in your glass bottle, you can't see any presence of this gas, because as soon as you take that lid off, all the gases escape. And that's exactly the same with the basaltic lava. It's all the gases, all the water and gases escaping. The volume of the water is not increasing to the point where the continents are being inundated with water. Is actually not keeping pace with the continents, and the continents are actually increasing their surface areas, which is contrary to what we're being told by climatologists, that the water level, that the seawaters are rising, etc., etc. It's actually the other way around. And an example, and that the actual continents, I explained in my first podcast, I think, the actual continental crusts are rising. I'll get this into a line, but as the radius of the Earth changes, the continents flatten. So at the outer margins, the continental crusts retain some form of rigidity over a period of time, and then you get earthquakes and then they gradually collapse and flatten to equate with the prevailing surface curvature. So when the continents are like this, the seawater is up here, and if they retain rigid, it appears that it's actually getting deeper and deeper. But once the continents flatten, then of course the sea level changes and exposes the continents. An example is here in Eastern Australia, the area around, say, Sydney, for example. Compare the sea levels, the change in sea levels in, say, Sydney to Cairns in northern Queensland. They quote that as Cairns is, the sea levels in Cairns is increasing at a faster rate than the sea level at, say, Sydney. But sea level is sea level. Sea level is uniform over the entire Earth. So it is actually the land that's changing, not the sea levels. They may rise and fall over time, because of the increasing surface area, but it's the land that's causing these differences in sea level changes from one point to the other. And they're determined from tidal gauges from one point to the other. But yeah, I'll leave it there, but I can get into a lot more depth than that, but it could just get too complicated for your listeners.
Okay, I'm going to see if this is a real question because I've read it a couple of times. It may not be. I don't know. It says, Dr. Maxwell, do you believe that isolation bifurcation of paleomagnetic volatiles were triggered by the Archean Cenozoic crustal resonance? Is
I
this a
have
real
no idea.
question?
I don't
Yeah,
know, but I have no idea what it's saying. It's
yeah, that's what
gobbledygook.
yeah, it sounds like it's gobbledygook, but I don't know. So one of the things that also is interesting about this kind of the expansion tectonics is that when the general public hears about it, it's somewhat shocking to them. And I know some of the people here that were on this call. One guy left. I know he does really great work in the area of quantum mechanics. They can't wrap their head around it. There's just something that it's so beyond. I don't know. I don't really know what it is, but I think it must be the same kind of reaction that happened in the 1960s, early 1960s. I think when people hear about it, I mean, when I thought about it, I'm like, oh my gosh, I'm standing on a ball that's expanding. And it's to me it was exciting because I look at it. I always, how do you say, like Aristotle, I always entertain whatever idea with an open mind. But it seems to really uh, 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 hit people like some people across the face, and they just totally throw it out as any type of
Can't
being able
comprehend.
to read. Right now, what do you've been around that way longer than I have? What do you think that shock is? What is the shock that hits these
Well,
people to
we're
make them?
fortunate. We're very fortunate at this period of time in that our media and our graphics is at extremely high level of competence with these young people come through and they can do anything with graphics, etc., etc. But back in the 60s, of course, our technology, I remember I was given, my father gave me my first slide rule in 1967, and that was it's virtually the state of the art.
Yeah,
And it
yeah,
wasn't until about 74 or something or other that I got my first HP 35, which was wow, a real wow factor. And of course, computers and whatnot were still not available until later in the 70s, 80s. And of course, by modern comparison, they're very primitive. But what I was alluding to is, and it's like Charles Darwin and Alfred Wagner sort of thing, and other very important people back in time. Copernicus, for example, they came up with these concepts, and when you think about it, these concepts simplify whatever their concept is all about. Global tectonics simplifies tectonics, simplifies the Earth. Basically, nobody uses plate tectonics except academia, and they only use it in academia to further the cause and to teach students. And student geologists virtually never use plate tectonics,
yeah,
whereas if you teach them global tectonics, they were able to use it because they were able to visualize, they were able to go in and look at outcrops, look at defined deposits and various this, that, and the other, and understand where that that particular outcrop or deposit was in time and space in relation to other continents around them, the climate, the fossils, etc., etc. And that is a very important aspect of geology to read the evidence, to read the data and the knowledge that's preserved in these rocks. And if you don't have the full picture, then all you're doing is having a very focused understanding, a very limited focused understanding of in your immediate environment. But with global tectonics, you can then apply that to further afield. And whereas with plate tectonics. It's a wham bang crash bang random process, and what you see here you can't relate to anywhere else because it's a random process, whereas expansion tectonics is an evolving process. So the difficulty, of course, is getting enough people on side to then educate the lay people to understand and to present this information, this new concept, this new science in a way that they can understand it. And basically, as I think you intimated in your introductions a few podcasts ago, if you take an orange, for example, and you orange skin, for example, and you stuff a balloon in there and pump it up, and then the orange skin will eventually stretch and eventually rupture, and the balloon will keep going, but the orange skin will remain there. And that's exactly, and you reverse that back in time, the orange will revert back to orange size orange. And that's exactly what expansion tectonics is all about. Exactly the same principle. The difficulty for most people is coming to grips with where this new material the new matter comes from to increase in volume. And that what I've presented here in my podcasts, I've tried to put across in a simplistic way that I see it, and I feel it's a very logical and understanding way to go forward.
Yeah, I think, I mean, you hear that constantly in even a person in our chat today was talking. I didn't put these up there, but I've been reading them, and it's like, well, this is all speculation unless you have a mechanism. And that, of course, that's what happened when somebody actually came back and said, well, no, it's observational. What all your observations
That's
point
right.
to one thing,
Yeah.
and it does not point to plate tectonics. One of the things here is I never asked you this question. It just sort of came to my mind. Normally, when you look at change, right? Look at change in the whatever field you're in. I mean, for instance, just to give an example, completely different. I'm on a whole plant-based diet. And then why did I do that? Is because I had heart disease in my family. And I found out they said it was genetic. Well, it turns out that me changing my diet to plant-based, my heart disease was reversed. Well, if it's the case now that we know that, for instance, Bill Gates does the study to find out that dye is the #1 killer in the United States, yet what's working against that? When I try to introduce this to somebody who has a disease that perhaps could be caused by what they're eating, I mean, just in general, there's all this resistance, and it comes from one place: money.
Mm-hmm.
That is because they have even if you have an organization like cancer, where 80% of the cancers come from what we eat. In fact, carcinogenic hot dogs are on the same list by the FDA here in the United States as a carcinogenic, the same place as plutonium. Yet, when you go and you try to talk about this, so there's documentaries about people saying, hey, let's look at our diet. All of a sudden, big agriculture, big science comes in who makes lots of money off of us being sick. And again, I'm not here to preach about that.
Mm-hmm.
My question is, can you take that same thing? Because it happens in physics in the same way. In cosmology, look at Halton Arp, who said, look, these galaxies and quasars are together, and redshift said they shouldn't be, and that's going to throw the Big Bang out. And guess what happened? His time on his telescope got cut, and time got cut more, until eventually he couldn't use the telescope. Is there a mechanism in geology today, or is it just really precarious? Because it sounds like today, it's sort of like relativity. You can't find anybody who makes a living at it. You can't find anybody writing their dissertations about it, but they all talk about it and they keep it going. Is there money behind this, or is it just now all just prestige?
I think certainly not in Australia. I don't think so anyway. To me, there's no money in plate tectonics. It's just academic, all academic. For example, I was involved with exploration in the Northern Territory to Western Australia, which is the central part of Australia, the other way, north west into Western Australia, probably over a length of about 800 kilometres. And I think I told you the story. Myself and my other senior geologist with me, we both worked at mines in the Northern Territory in the same area, and our job was to map and extend exploration northwest into the West Australian side. We eventually found mineralisation, and it's now another gold mine up there. But anyway, what we were finding is the mainly sedimentary rocks plus some volcanics with it, and we were finding the same sediments throughout this 800 kilometre region. It was the same sedimentary basin, but it had been. It was also an active orogenic zone. An orogenic zone, I can just explain it. There's a zone which is gone, which is like that, and faulting at
Right.
subvertical faulting, crustal scale faulting over a width of about 80 kilometres. And where each of these, the mines in that region, where each of these faults cross-cut some particular strata, volcanic strata, that's where your mine was. And I was able to apply this, and I have a mine named after me because I found a mine in that area. There's only
But
600,000.
now we're talking about money. Do you got money coming into your bank account from that?
No,
Sure.
I was only contractor. But anyway, what I was alluding to was both myself and my other senior geologists were seeing the same thing throughout this entire 800 kilometre region, and we were exploring from one end to the other, a number of different companies. And anyway, one of the companies, another company in the area, had a young PhD student, a recent graduate PhD. It was actually the company I was working for, had this PhD student come in to give an alternative viewpoint. And his PhD was in the Northern Territory part of there, and he'd come to the conclusion that this was an ancient, small ancient crustal fragment which had come across and banged into wherever I am, banged into Australia, like so, fused. And in theory, both of these crustal fragments should have been totally different. But what my offsider and myself was seeing is we could map across this particular fault zone, 80 kilometre wide fault zone, and see the same rocks from one side to the other. So that disproved his theory that this was a classic plate tectonic collisions setting. But he wouldn't have a bar of it because he did his PhD studies on plate tectonics, and of course he couldn't back down. But anyway, that was my story.
Yeah, I mean, it is truly amazing. I think what you're saying, and just to sum it up, is that there really is no money interest behind it because no one's making anything off. It's very similar to, in fact, here I'll put this comment up here. It says this guy says, I think, or a person says, I think the oligarchy is maintaining the supremacy of Einstein's bogus physics and quantum jive. Growing Earth would mean overturning that, and I. Yeah, and it's different, for instance, from stuff with diet. Diet, for instance, is food and medicine, and there's a lot of money to be made in making people sick and giving them medicine, and people are profiting off of that. That's a different stranglehold than these people have. I think this is more precarious in some ways, and
This is identical to Charles Darwin. It's identical to Charles Darwin. It was the church that stood to lose out of that confrontation, whereas Charles Darwin was just presenting observational data,
Right.
observation, came up with a new theory. But yeah.
Right.
And same with
Right.
Copernicus.
Right. And I think, the more I think about it, I'm thinking to myself, what would thrust this into, prominence? I mean, get eyeballs on it. And I really do think if we could get together, young people and I know you've been trying this, but I think we need, I don't know, I'd be happy to put together a group and try this again, because I work with computers. That's my job. And I know you and other people have been working on or looking at making computer models. If for some way we can take a global Google Earth and be able to change its radius and be able to map things onto that, I think if we were to be able to come up with an open source, um, you know, database that would be able to be plotted upon a growing sphere, a growing Earth, where people could go and put those layers on it and make this accessible to people. I think that people would go in and start doing that. People like your friend who was the nut tree guy, right? He'd be able to get in there, make a login. The question is where does that come from? To do that from a grassroots, you know, group of people without any funding. Now, if we were to get funding and be able to get programmers to just jump through the hoops that we need and create that and create a website so anybody could log in, create a their username, and then start to be able to put their own layers on that, so that study. So what you would have are you would generate a massive amount of new interest in so many areas that really are sort of dying. The only area I see in paleo anything are finding new dinosaurs, and that's becoming like we found so many, and you find another femur the size of two people standing up, and no one ever questions whether or not these animals could ever survive in today's gravitational field. But I mean, just the amount of interest that people would in the natural world be able to walk out and from flora to fauna to the geology again, to physics, to cosmology. How do we explain this? Can we come up with real ways to reproduce this? Or I mean, it just seems to be something waiting to explode. And I think if we could get a couple $1 million from somebody, and or a grant that would allow us to come together, get programmers, lay it out, because again, I'm a software engineer. I would just I'm busy doing my stuff,
it's
but
doable. It's doable.
yeah, it's
because
doable.
they do it in the graphics industry all the time with
Of
their
course,
movies and whatnot. But um,
I
what
think that
I
would generate a huge amount of interest.
yeah what I've found is um, conferences, for example, just do not work. What
Right,
we what we It's a gathering of like-minded people,
right.
generally now elderly, and they're pushing their own wheelbarrow,
Yep,
which is I don't know if you have a term there, pushing their own wheelbarrow.
yep,
Um, and they're just saying the same things over and over and over again.
right,
And I've been to a number of these international conferences all over the world, as you probably know, and
right, right.
they just don't generate any interest, and you don't get across them. So my thoughts are that exactly what you were saying is get together, to get this stuff in a Google Earth type form
Right,
where people can interact with it.
right,
I have a
right,
long-term ambition, and I'm not a computer scientist or anything like that, whereby all my models are in a Google Earth type format. Um, the particular researcher may have found a new dinosaur fossil, as you mentioned. I'll plot it. Oh, there it is. Okay, and there's a database of fossils. There is an international database of fossil locations, thousands of them. I think I plotted 10,000 of them on my models, and on my next podcast I'll show you a selection of them. But okay, here are all the existing locations, and this is how it relates to that continent there and that one over there. And this is where the ancient sea was. So therefore, this dinosaur that I've just found lived in a near-shore environment with lots of, which in tropical environment, lots of vegetation, ferns, and da 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 da. And that, to me, that it'd be invaluable to geography and paleogeography and those particular sciences. Not necessarily the actual, say, mineral exploration history. One of my early on, I was aiming my promotion towards the mining industries, but plate tectonics and expansion tectonics are not really relevant to a mine scale scenario where they're focused on finding the next ore body, finding extensions on existing mineralization. They're just not interested in knowing where that fits globally, da 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 da. Having said that, I did work in international search with Newcrest Mining there for a number of years, and I was able to plot not discoveries, but mines, existing mines and exploration prospects from all over the world onto my models, and I gave a demonstration to my peers to say, hey, look, this is how they all fit together, sort of thing. So that was just a friendly interaction, and they were quite impressed with it. So so it's a matter of getting this information out to enough people to start then forming that cascading, rolling motion to get it promotions. And
well,
then,
if you look, yeah, go ahead.
Sorry, and then to overwhelm plate tectonic. Plate tectonics cannot offer, they just can't offer anything to the general public. It's just a hairy-fairy, la-di-da theory out there in academia land, and the average person in the street just can't comprehend it, accepts it because they can't comprehend it. Journalists and writers such like are the worst people, because they just run with that stuff and bring up all this movie crap with this asteroid and cracking continents and all this. I just go, oh no.
Right.
That happens, but so focusing on the younger so this technology literate younger set, so if we can get it out and promote it, then that's the way to go.
Well, you have to look at today. You have to look the way it works. So if you look at, I'm getting echo on with somebody. I'm going to mute you here just real quick. Okay, because that way it's not going to echo there. So what I think one of the things is today is how's the world work? Like you said, you have conferences and conferences. They actually are good. Like when we have our conferences, it just gets people together to be able to discuss face to face, and it's a lot different than when you meet online. So if you are trying to find like-minded people, that's one thing. Now, trying to get it out to the rest of the world is a whole nother endeavor. And the way I look at it is, if we had the ability, the way it works today is people have open source software or things that people can use. And that's what Google does. For instance, if we could find and get somebody in Google interested in this project, that is, here's the software, and to get some young mind who looks at it goes, ooh, this looks really interesting, then put together a team and then to try to direct this. Now, whether or not we would have to get actual funding for it, you can even do that online. You can make a project. So I think the first step would be is to look out in the world, form people, to put people together. We have a lot of younger people in our group, a lot of software people in our group. In fact, numerous. Lori Gardia is one of them, and she does a lot of work with software. Jeff Yee, who has his own theory of how the universe works. He also has people, maybe he would know, but we would be able to try to put together a committee that who the idea would be meet regularly and try to come up with, here is the software where we could look to work with, like Google. Can
Google
we
Earth does work.
Can we
Google
model?
Earth works very well.
Yes,
I've
but
draped,
they don't have this size change though, do they? Do they have the?
Exactly what I was about to say. I've got my earlier models, which don't include the continental geology, my early models in map format, and I've been able to drape that directly onto Google, and I'll send you the links to them to see. And you can actually rotate these around on screen. But what you're doing is you're just retaining the constant size Earth, the Google Earth size, and just draping your maps on that. So your maps are increasing in scale, decreasing in scale, whichever way, but the Earth is staying the same. What would be ideal would be for the Google Earth to change in size back in time
That's what I'm saying. Yeah.
and
And
drape the maps.
what
And it's beautiful. They're actually beautiful maps. They work really well.
now saying is because I work with open source. In fact, my friend and I have just put out into the real world a computer programming language in the open source world. And what happens is if you get people who are interested in that open source project, people will contribute to it. Now, if Google Earth, I don't know enough about Google Earth software to know whether all of it is available. Because if all of it's available, all the code, sometimes you have the ability to use it, but you can't get at the engine for it. If you get the engine, you could then go in there and have somebody modify it so that you could change the radius. Now, if you can change the radius, all you would have to do is have a scale there, and you would literally take the Maxlow sizes and have it so that when you're looking at it, what happens with software? This is the way it works, just the way it works. Let's say all of Google Earth is available, all of its code, meaning every line of code that makes that thing work is available. You then go to GitHub, which is a place where all open source software is there. Anybody can get it. What you do is you fork off. Fork off means you make a copy of it in your own little world in GitHub. Now I can modify it. I can change the rate. I can do anything I want with that code. Now, if it's a case that we would fork something off of Google, the world, that is, fork another branch. It's just like evolution. Here's a new branch, and that branch would take and add the ability to change the radius. And the radius then would be scaled, right? That you would say, okay, we know these. Then what you would do is that you would have to make it so that everything you plotted on there would be related to a time. So when you plot something, all you would have to add to all those plots that James Maxlow puts on there or drapes on there, a time stamp
Yeah.
of when. And then what happens is when someone would go into this newer version of Google Earth and they were going to see, they move it back, they're going to see the plot of what you have on there as there. And what we would do is you would just keep that plot even though it would be shrinking. Then eventually what would happen is that you would add one more thing to that model, not just the changing of it, but to be able to literally put dots on and outline coastlines, areas. So what happens is when you put that area there, you can then make the area, when it goes smaller, you can make that same area. You would label those points to be the same. And so when you would flip between those, you could even write an interpolation, meaning what happens is if I make this a continent and then I make one smaller and I go and I put all the little dots on that, I can make the computer make the tween it, what we call tweening it, making it in between. So those two modifications onto this software would allow us to build a Google Earth where you could not only change the shape and plot stuff on it, and those plots would just have a time frame. So, and then you could, move the slider, but you could eventually, instead of draping things over it, go in and make a layer on there. Just like you can go into Zoom. I can get my phone on right now and go into Zillow is a program for houses, right? And if I want to go onto a map, I can literally on my phone draw an area. That area is remembered by the program, and then it goes and finds all the houses in that area that I'm interested in. Now, those things are totally possible. So there is a way that we could come up with how to do this if, and that's a big if, Google has every line of code available for their Earth. And and all we would then do is have to find people who could actually program that. Then what we would have is you'd have a website, on expansion tectonics, right? That's what you call it. You would then have it hosted there, on a server where all the data's sitting, and then people can go in, create their login, do what stuff. You plot stuff on it. You would make even areas. So your area interpretation would be maybe different from another's, and then all the people could argue about, what's better and see that. I mean,
Mm.
that to me would break it open because all of a sudden you've got a place where any Yahoo can log in, look at it, change it around, get the idea. And when people start seeing that working and people's interest come, young people, then all of a sudden you've got paleogravity as a degree at a university. There you go. I solved all the problems. We no longer need James. James, thank you. We don't want you to speak
You
anymore.
do
I've
need
solved everything. No, I'm kidding.
you do need my formula. You
Oh,
do
of
need
course you do.
radius
Absolutely. No, believe me. That's
incorporated.
always no, no. I'm sorry, but you can't extract yourself from what you've done for the world. No matter what you would want to do,
I think
you could go nuts. You could go nuts and become loony and do something stupid, but it doesn't matter. You've already given us what you've given, so you can't take that away. It's in a
yeah,
book.
I think
So,
on my webpage, the work that John Eichel has done for me on
right.
that webpage is brilliant, and that scroll up and down the time frames, and it just they're
Right.
only static images, but it brings
Right.
up all all the globes, and you get the sensation, that the impression that it's changing radius and
Of
time,
course. Of course.
and plotting the same information on that. That's a very it's a lovely, very interesting way of displaying it, but it is crude compared with what could and should be done eventually.
Yeah, I think what I'll do is on the last talk, what I'll do is I'll maybe actually you could demo that, right? You
Mm.
could put that on your screen and show people, after your last talk,
Yeah,
so people can get an idea of that. But I truly do think I'm going to investigate. I don't know if anybody here is taking a look, but investigate if the idea of making this type of open source project, forking off a Google Earth and going from there. Uh, there may be other programs that would be available, but I think that would be the best because it's sort of and then try to check people out. Try to I can go snooping in the software world and try to knock on some doors of people who are in charge of that. Maybe they don't have to necessarily agree with it, but maybe they'll think, oh, this is a really interesting project, regardless of whether they agree with it, right? I mean, a programming challenge to do that. The modifications aren't such a big thing, and then if we can get a open source and a group doing that I think, and then worst case, we can always find out that it's totally doable. That maybe we don't have the manpower to do it, and then at that point, you use something like GoFundMe or Patreon or whatever to then have
it all
people
comes back to
don't.
funding, doesn't it? It all comes back to funding.
Yeah, no, but it doesn't always. Not always, because we are doing an open source project, and many open source projects are done. Or people are programmers. There's a lot of coders around the world. People
Mm.
who program in programming languages, and we are they'll come in and I'm a part of a supercomputer group with the supercomputers available to everybody to use. You can download it and build yourself a supercomputer, and the thing is that we have people contributing to that who are not being paid to do that.
Mm.
And so those things exist. And I think if we put together all the pieces and have what we have and a way to modify it available, we'll see if we can do it just with our volunteers, or we may find out, okay, let's get some programmers. How much money do we need to have them do these tasks? Because on GitHub you can say, do this task, and if that task gets, we can get some donors. Maybe we can actually have some programmers actually do that. So that's a possibility. Let's see here. We have anybody raising their hand that want to talk to directly with in our green room, want to talk or question or discuss anything with Dr. Maxlow. I do see him. Again, what I would ask is that people, try to keep this to expansion tectonics. The idea is to keep that on point. So I saw Steve Scully, so I'm going to bring him up. And I don't know, Ian, did you raise your hand as well or no? He did. Okay. So I'm going to bring some other people up here. Let's bring up here Steve Scully. Hey, Steve. Let's see, make sure he's. There he is, and we are with the famous James Maxlow. You can always say, when you're in '97 and he and I are gone, that you talked to a very famous person, and it wasn't me. So go ahead and make your comment. Or
Well, I mean, I come from I'm a engineer, but I have a physics model, and I come from that angle where essentially what I concluded through physics was that magnetic fields are particles that travel in a figure eight orbital pattern. And so what that means is that these particles merge at the center of a body. And so part of I've kind of, when I was exposed to expanding Earth, I was like, well, clearly it expanded. And I think that the mechanism is related to that. The Earth is essentially, when the Earth rotates, it causes a vortex of this flow of ether particles that merge at the center. And that produces what we observe as the inner core. And then that essentially produces, I was leaning into it, produces matter that then like build up pressure inside the planet because because of this production of mass. And so it essentially at some point reached a point of instability where it fractured, and evidence is everywhere. And so I just wanted to like throw that out there because I haven't seen anyone talk about that concept of a figure eight of orbitals, which is important because it's how gravity causes a magnetic field, which is tying fundamental forces, and it relates to this. So I think I just wanted to point it out, just see what you guys think, because I don't know how tied you are to like the specific mechanisms. I mean, I've looked around.
Yeah, I've been through all of it, essentially all of the mechanisms available. One of the things that we have to keep in mind is, well, there's a number of options. You have a constant mass, or you have a constant density. Density equals mass over volume. You change your volume by changing your density or changing your mass. Retaining a constant mass, for example, means that your density is just enormous during the Archean. Something like 50 times what it is now from memory. Same with the surface gravity; it just becomes unacceptable. So, in my modelling within my book and research and thesis, I eventually adopted a constant density scenario, or constant density to slightly changing density, and the changing mass over time. Because in order to increase mass, you have to have input of material, input of your primary particles, and I presume your ether you're talking about is the same as your plasma. So electrons, protons, and all the various particles involved with that. All I'm, as I mentioned in my previous podcasts, I'm magnetically attracting solar particles that originate from the sun into the Earth itself by the auroral polar regions, and generating new matter within the core mantle region through that. So how that fits with what you're saying, I don't know.
Boundary. So at the boundary rather than at the center, though.
Yes, that's right. The D layer, essentially the D layer, which is a highly reactive layer. So that's
so
at
the
the
D
core.
layer, what I think it's just to let people know, D layer is a layer inside the Earth, right? There are
Yeah.
certain places, mantle and going down core, D layer.
Okay,
So
core
what?
mantle,
Right.
upper, middle, and lower mantle, and then there's a D layer before you get into the actual core itself.
Yeah.
And that's a highly reactive region through there. And that's where I speculate that matter is being generated from the input of these solar solar wind related particles, plasma,
So I
ether.
think one of the things is, Steve, is that we, as people interested in physics and models of the universe, my father and I have a particle model where we don't deal with this a whole lot. But you have to start thinking, okay, if this is what geologists are thinking, who really study this, how can that be explained? And one of the things that Dr. Maxlow came to us was, how do he wants to know if what are some of the ideas? How would this work? And it's really still open. It's an open book. I think the idea, a lot of people do agree with the idea that the sun is blowing things apart into atoms into subatomic particles.
Yeah.
And then there are ether models, there are particle models, there are lattice models. There's a lot of different models even below that. And the way I look at it is every model of the universe. We have a model for magnetism, electricity, gravity, and light. I mean, we do. Those models are going to have to deal with this because these things, the idea that the Earth isn't gaining in mass is really hard to dispute. The
Yeah.
observational evidence is just way too big. So we have to get over this idea. To me, it's like people say, "Oh, I can't accept it." To me, it's like, no, this is a great mystery we can solve, right?
Mm.
And I think the idea of us, one of the things we could even do is to have maybe even a session of people. Maybe I'll get all the people who have an idea of how mass could increase, and we could have a presentation. Each person will put forth their ideas and just see what's going on.
Okay.
So I guess what I'm seeing from you is that, and I know there's a lot of the people that have been chomping at the bit to talk about their idea of mass increase. And the reason I don't do too much about it is because we want to talk and focus on the evidence and Dr. Maxwell talking
Yeah.
about it. But I'm really thinking we've got so many people wanting to speak about that
Yeah.
yeah,
Finish this.
yeah,
I'm
sure.
sorry, but I just please please.
Yeah.
So you're saying though that it's forming at the D, what is it, prime layer? But the
Mm.
thing is, like, that's not where the focus would be. So first of all, when I say ether, I'm talking about smaller particles, like infinitesimal, down to nothingness. And they're so small that relative to them, Earth is infinite in mass. And so basically they're stuck in an orbital. They're not coming from the sun. The sun is sending out bigger particles, more massive particles, ones that don't make it through, like a neutrino. And these smaller particles, though, like they merge at the center, exactly at the center. And that's why there's an inner core, because of where the electromagnetic field merges. I'm just saying, I feel it's important because it's where the focus is. Whereas if it's at this like shell, there's no focus. The focus is like at the center.
Yeah, and I think what in the end, what I think is what we have to understand is there's going to be a lot of different people with a lot of different models about how to explain this, and I think that is, they're open for discussion, and I think we're going to have a place to do that because that seems like James, like a lot of people are have their explanations for that. But thank you very much, Steve Scully, for coming on. I know, Ian, did you want to come on real quick? Is it something urgent, or you didn't want to? Yes, no, yes. Okay, I'm going to
Ray,
bring him up.
I,
Go ahead.
I had a number of points, but the time is short. So just one point, perhaps, James. I'm just wondering if in your analysis over 4.5 thousand million years, you've taken into account the secular variations in the orbit of the Earth over that period. For example, things like precession and nutation. Have they become apparent?
Probably, but I haven't done anything about it.
Okay. Well, I think that's fairly brief.
Yeah,
brief.
so I was a bit brief there, but I think because I'm changing radius and the size of the Earth over time quite considerably, how you go modelling this, I just have no idea. So I'm too involved with and my timing and whatnot, too involved with the geosciences rather than getting involved with the the astrophysics and all that sort of physics involved.
You have looked at the magnetic variations. You had a slide on that.
Yeah.
So that really sparked my mind in regard to other phenomena which have changed over time.
Yeah. I've simply used the existing databases, the international databases of the paleomagneticians to determine the poles and whatnot. There is evidence in the distribution of these ancient poles to suggest that there is precession in that the fact that in each of the model, the data plotted on each of my models was a 25-degree radius in the distribution of this data, which is exactly coincidental with the present-day Earth, where there's a 25-degree distribution of ancient magnetic pole plots, which suggests your precession, etc., etc. So there's evidence in the modelling of the pole data to suggest that that occurs back in time, but to actually model it, it's just well beyond me.
I think one of the things, Ian, that I can say, it was pretty interesting. I first started in physics dissidence back in the early 90s when I met a physicist from Argentina who showed Einstein wrong, special relativity, also why the neutrino was postulated and that doesn't exist, all those kinds of things. But one of the interesting things from that, and his disputing of the special relativity and removing the problem with it and then coming up with a Newtonian answer. One of the things that came out of it was he talked about mass increase. And one of the things that special or general relativity or special relativity was supposed to explain was the perihelion advance of like Mercury. And of course, if you do the calculations, it doesn't really fall on it. But what his explanation was, way back, this is about 20 years ago, was that mass was increasing. And this was before I even knew, James, about expansion tectonics. This is a physicist who explained the perihelion advance is sort of the way, you know, the elliptical orbit doesn't stay in one place. It's like, you know, in the change in that, James, is not Newtonian, it's not Keplerian. And so the idea was, well, we don't have an explanation using Newton, so there must be something going on. And relativity was supposedly came and solved the day, but it didn't solve the day because it only did Mercury and it wasn't that close, actually. They fudged it. So here was a physicist who came up with the idea of mass increase, then said and showed in calculations, I don't have those, how that was for instance, the Pioneer slowdown. The Pioneer spacecraft is slowing down. This physicist said, well, as the solar system is gaining some mass, you know, that this was happening. So it was interesting that actually a physicist related this idea of mass increase to orbits and came to that conclusion without knowing anything about expansion tectonics.
He wasn't talking about mass increase, David, with speed. He was talking about, you know, absolute mass increase of planets.
Yes, he was. And what he was saying, it was because he believed gravity was caused by a force and that no force could be magical. It's got to be created by some type of particle. Now, whether or not what that was, you know, like a graviton, that was something. But
actually, incidentally, there's less than 0.1% difference between the calculation using Newtonian mechanics of the advance of the perihelion of Mercury and what we actually observe. So it's a very small amount. It's sort of blown up, you know. People say, oh, Newton says the thing doesn't possess at all, and general relativity gives you this magic figure of 43 arc seconds per century. There's actually over 6,000 arc seconds per century observed from the Earth.
Yeah, and that happens a lot where you have these small, minute things that people get all hissy fit, you know, about. The same way can be looked at as the dark matter, which they throw out there, right? Dark matter exists because we can't explain the speeds of the stars at the edge of a galaxy. It turns out that it's because we are treating the galaxy as a sphere, and when you do that, Newton explains it. We have several people in our group who have explained the speed of the stars using Newton. So, any other comment before you go here, because we're wrapping it up?
No, thank you again very much. I think that's the second lecture.
Midnight.
I beg your pardon?
It's past
It's
midnight.
just
He's got to go by
midnight.
bed. Yeah, he did.
Thank you.
Okay. All right. Thank you very much, Ian. And I do want to say very, very much thank you so much again. Go to bed. I will see you in a couple weeks. We
Yep.
will we will have somebody else on here, but I want to thank you so much again for these presentations. If you happen to miss it, we do have it recorded. But I'm going to say good night to you and then sign off so you can go to sleep and do a few wrap up a few things before you go. But thank you so much. Did you want to have any last words, or are you just good night?
Good night.
Okay, good night. Thank you so much.
Thank you.
Thank you. So again, I want to thank everybody from the Dissident Science Channel for tuning in. Also from the John Chappell Natural Philosophy Society. If you want to go to our YouTube channels, you can by going to youtube.naturalphilosophy.org. Or you can go to youtube.dissidentscience.org and you can see our channel and see all these great videos. This one's being recorded to both of those channels simultaneously and to this Facebook page as well. If you haven't checked out our websites, you should go to naturalphilosophy.org. You can join in amazing conversations about amazing subjects where the best critical thinkers in the world do meet. And if you're new to it, you can go to sciencewoke.org. It is the only online magazine for critical thinkers, and you don't have to be a PhD in physics to read these articles. They're very easy to read and very interesting. And of course, I'm going to put up a few videos here just about our organization. So here we go. So yeah, check us out. There's a lot of great information there. And of course, what did I do? I forget the stinger again. So I'm going to put this up. This is James when he goes back and watches it. This is what I'm supposed to put in the beginning, and I always forget. Well, the good news is next week we're going to be having Dr. Glenn Borkert. He's going to be talking about infinity. If you don't know about infinity, you need to know about infinity. Why? Is because in fact, a lot of the new models of the universe do base themselves in the infinite universe model, meaning there is the smallest particle. My father and I, with our model, the particle model, we also subscribe to that. And so if you don't know about it, check it out. It's going to be next, I think this November 7th, I believe, at 10 a.m. right here. You don't want to miss that. And then after that week, we'll have James Maxlow on his last talk in his series about expansion tectonics. And right after that, we're going to have another, I think maybe 2 weeks after that, we have a talk by Dr. Glenn Borkert. And I'm also looking to have George Coyne back on and talk about the Big Bang. But actually, Borkert's going to be talking, his second talk is about the Big Bang. Whoops, I forgot that. And so if you are a person who's thought about the Big Bang and all the problems the Big Bang has, well, we're going to be talking to Glenn Borkert about that. And of course, Steve Bryant's going to be coming on in his Disrupting Physics book. If you haven't checked it out, look up Steve Bryant and read his book on disrupting physics. He gives an alternative to relativity and just shoots relativity down, even though this Facebook page has 20 million viewers. Anyways, thank you so much, all of you, for your patronage. Remember to join our organization, go to naturalphilosophy.org. And you can go to that. Here we go down there, naturalistance.org. Join our organization and consider becoming a paying member. It's only $35 and on up per year. You can donate to what you want. It's greatly appreciated, the donations, because it keeps us going and keeps shows like this going. So please consider that. Your patronage is very important. And if you are a member of our group and have been for many years, please make sure you log in and sign in new to our new website, and make sure I'll put this up there. This is it, and get yourself signed in, get your profile made, and please consider getting your membership. It will renew annually and remind you, but like I said, it's greatly appreciated. And of course, I'm Dave D. Hilster. I am your science therapist, trying to get you to the promised land of becoming a critical thinker. Don't listen to anything I say or your professors or the university. Stay thinking, stay critical. I'm Dave D. Hilster. Ciao for now.